Welcome to ES350 Lecture 5. Today we're going to continue our work from Lecture 4 by turning the functional analysis into a basic model, which is the third use of the functional analysis we talked about last week. We will then use that model to predict output for our devices in order to finish filling in the QFD, which will allow us to make a final decision about our device. Couple of announcements and reminders. Yesterday you had your brainstorming FA due, which was a team assignment, so you should have one tab in your DMADver that you turned in for brainstorming, and then you had your FA for each device idea, which was an individual assignment, so you should have one tab in your DMADver for each of your team members, which has a unique device on it in terms of functional analysis laid out. The team peer assessment, which is on CATME, has been posted. It's due next week, so you should have gotten an email from CATME. If you didn't, check your junk mail. If you can't find it, let me know and I'll make sure I get it resent. Today we're going to work with the functional analysis that you created last week and turn that into a basic model. These will also be individual, so you'll have another set of tabs for basic models in your DMADver, one for each of your team members. And these are due next Wednesday. So let's talk just briefly about what we mean by modeling. So in engineering, the term modeling can have many definitions, especially within design. So within a design process itself, people could use the term modeling to mean three different things. One is creating the CAD model, which we will be doing later in this process. That is sometimes called modeling. You can also create a physical model, so you can create a prototype and something of that sort, and that could also be called a model. What we're referring to as modeling right now for these purposes is the creation of a mathematical description, a mathematical model that will allow us to simulate our device, and so we'll be able to predict the behavior of our device. It'll help us answer a couple of questions. For example, using this model, we should be able to answer the question, what outputs are possible? So if we look back to our CTQ and we figure out what our customers actually want out of our device, can we achieve those outputs? And what kind of inputs are required in order to achieve those outputs, and do those inputs fit within the CTQ? So for example, if you want a certain output of a pump, a flow rate, right? Well, you can set your model up and say, okay, well, I need 50 gallons per minute, whatever the flow rate is. What kind of force would be required in order for me to get that? And then you can look at that force, which should also be one of your customer requirements, saying it's easy to use, therefore it requires less than 5 pounds. And you can tell then, can my device actually achieve both of those requirements? So in this class we're going to do two different models. We're going to do a basic model and an advanced model. Right now we're doing the basic model. The goal here is to help us fill out the now section for our QFD, for all of our possible ideas. So take a look at your QFD, figure out what numbers need to be filled in there. That's what you're going to model. So that's your goal. For the basic model, you can ignore losses. You're coming up with a rough estimate. So you can ignore the fact that things aren't actually constant. You can ignore the fact that there's friction, there's losses. But the general idea is to try to convert your inputs into your outputs. Later, once we've picked a single device, we're going to turn that basic model into an advanced model. So we're then in the advanced model, we're going to be looking at losses, we're going to be looking at efficiency, we're going to be looking at possible failure mechanisms. The goal of the advanced model is to help us actually design the device. So to help us pick the gear ratio, to help us pick the shaft size or the shaft material. So there we're going to be much more specific and looking at very particular aspects of the device. Right now we're worried about turning our inputs into outputs, and we're working with rough estimates. So this is building on what we did last time, all right? So we started with the functional analysis at the brainstorming level, right? So if you remember the example I did last time with collecting rainwater and turning it into drinking water. So at that level, we had the action words in our boxes, right? Things like collect, transport, filter, those types of things, right? Then we moved on to the analysis FA, right? So there we brainstormed all the different ways we could collect water. We brainstormed all the different ways we could filter water, and we picked one for each of those boxes, and that became our device. So now in the box, instead of the action word, I have an actual component. I have a roof. I was going to use the roof to collect the water, right? And the roof will do certain things. It will convert a distributed rain into a volume. So that's what the function of that roof is that I'm interested in. And so we have an input of a rain weight, we have an output of a volume, and we have control variables, like the area of the roof. The control variables, again, are things we can control in the design process, but once we pick them, they're not going to change from use to use. Now we're going to take that analysis FA and turn it into a modeling FA. So now we're going to have the roof, and instead of just saying we're converting from distributed rain to volume, we need an equation. Volume is going to equal the rain rate times the area times the time. All right, so then the inputs are going to be the rain rate and the time, which are things that could change from day to day, from use to use. The area is the control, right? That's coming in the side, and the output is the volume. Then we're going to model that FA in Excel. So we're going to use the functionality of Excel to actually code that equation, and we'll be able to enter in different rain rates and see what happens to the output at the bottom. So what we're focusing on today are these last two boxes. So here's an example of a bicycle functional analysis. So this is at the analysis level, right? We've got human energy going in first, and then we get an output of that is the force on the pedal, right? And so then we have a pedal system, so we're putting a force on the pedal, and we're getting some sort of torque and angular speed out of the pedal, right? And the input, the control variables for the pedal were number of pedals and the crank length, for example. Then the torque from the pedal goes into the sprocket, and that is then converted to a force on the chain and the speed of the chain. Then we look at the chain, and we've got that force and speed on the chain, and the chain is going to turn that into torque and omega on the rear sprocket. And then we look at the rear sprocket, and that's going to turn that torque and omega into force on the wheel and speed of the wheel. And then we look at the wheel itself, and that's going to have a force on the ground and a speed of the overall bicycle, right? And so that's the general functionality of the bicycle. Now your functional analysis might not yet be at this level, but in order to get it into a mathematical model, you may need to move it to that level. So if yours is at a higher level right now, that could be fine for the analysis level. But if we're going to turn it into a model, you may need to get in a more deep level there. So then we take that functional analysis, and we're going to turn it into a mathematical model. So here's the Excel document. We've got the functional analysis down the left-hand side. That's what we were just looking at. And then we have some Excel boxes in the middle, and then over on the right-hand side we have a model explanation. And this document is posted to my Wartburg. I'd highly recommend taking a look at it and modeling yours after it. So we start in the functional analysis with a person and their legs. Those don't actually go into the model because we are not modeling like calorie intake and how many calories are being burned and things like that. So we are starting our model with the pedal system. We have some sort of foot force, and we have a velocity of that foot, and those are the inputs to that system, the pedal system. And so in Excel, we have these boxes, one for each of those functional analysis boxes. So we have the pedal system going to the front sprocket, going to the chain, going to the back sprocket, all the way through. What we have there are input variables, control variables, and output variables, like we had before. You can add more. There are 2 boxes for each of those right now, but there's no reason why you're limited to 2. So you could very easily just add more inputs, more controls, more outputs. The yellow boxes are the ones that you can change. Okay, so those are the things that the user of this model could vary. Notice, for example, in the pedal system, the force is something we can vary. The velocity is not. The velocity is a coded variable, because the way this model in particular is set up is we enter the force that we're allowed to create. We go through the whole model down to the bottom, we get a speed, and then we feed that angular speed of the bicycle back up to figure out how fast the person would have to apply that force. All right, so that's VF in that first cell. So VF is an output of the model, even though it's an input to the system. So things get a little bit confusing there when we start using the same terms for things. But the general idea is, to use this model, I'm going to say, well, I have a person who says they can apply 75 newtons. How fast would they have to apply those 75 newtons to get this output down at the bottom, which is also in the yellow box? We can't see it, it's cut off. But to get the bicycle to move a certain speed, right? Which is another thing we're specifying this in the CTQ. And so then it comes back up, and then the question we ask ourselves is, well, is that a reasonable number? Can somebody actually move 1.667 meters per second? Okay, so the yellow boxes are things we're going to enter. The other boxes are equations that are coded into Excel. And so we have the pedal system, we put in the force on the pedal system, we put in the number of pedals and the length of the arm, and that calculates then for us what the torque and the omega s is. The torque and omega s are then inputs to the next box, right? So those are just equal a reference cell. So if it changes up above, it'll change down below. And then then those work through. So then we convert those TS and omega S to a force and a velocity, and so forth all the way through. We also specified what equations we used. Notice the variables we're showing here in the equations are the same variables in the chart. Those variables should also agree with the tab before, where you had the functional analysis laid out in the table. So keep using the same variable names so that everything stays consistent. And then if there are assumptions, we're writing the assumptions. So for this bicycle, we're assuming that that the force and the pedal arm are always perpendicular. Obviously, that only happens twice in each cycle of a pedal. But this is a basic model, right? We're making assumptions. We're getting a rough estimate output. Make sure that if there are assumptions that are applicable to multiple people in your group, that you all make them, so that you're actually comparing apples to apples when you compare your models. And then over on the right-hand side, model explanation. This is the text that explains what's happening at each step. So use that as if you were sitting there in front with me or with your group member explaining how your model works. Okay, so that's where that would go. And so once again, take a look at this file. It's on my Wartburg, and use that as a model then for how you're doing your own basic model. A little bit more on Excel coding. Make sure that you're linking cells instead of entering the same number in multiple places. If you haven't used Excel much, talk to me, talk to some group members, and see if you can figure out how to use Excel to code this. Just like in the bicycle model, you can model from the top down or the bottom up, or some combination of that. So for example, we modeled the force top down. We entered it at the top and we got a torque down at the bottom. Whereas we measured we modeled the speed bottom up, where we entered the speed we needed, and it calculated how fast we had to put in our input force. And so that would be an example of a combination. You can decide which way makes sense for you. If your model has multiple functions, or if your device has multiple functions that aren't necessarily in a chain the way the bicycle is, you could have boxes that aren't linked to each other, and that's fine. Just be clear in your explanation of what's being modeled in which box. Make sure you're using the same variable names in the list, in the equations used, and in the functional analysis on the tab before. And watch your units. Make sure your units are compatible, that you're converting between units correctly and things like that. Some resources for your models. This is where you're showing off all of that material you learned in all your classes. So it depends on what you're doing, what your device is supposed to be doing. But equations from statics and dynamics might be useful, equations from fluids or thermo, things from physics, things from electric circuits, right? So go back to those past classes and those textbooks. Use the web as resources if you're really looking for something and you're not finding it. So like, for example, if you're grinding grain, I have some resources that may help you figure out how much force is needed to grind grain, things of this sort. And talk to the experts. Talk to me, talk to Dr. Black, talk to Dr. Ben or Dr. Figura about physics type things. Talk to other people who may know numbers and things of this sort on how things are working.